Hi everyone, welcome back to section 1.8. And right now we are working on part 2. The thing that we want to work for is looking at the domain and interval notation. And we have three different functions here. We have s of x, which is a rational function. And what is a rational function? Well, a rational function, you have to look at the denominator. You are not allowed to have a zero on the denominator when you have a rational function. So when we're looking at the domain in integral notation, the denominator cannot equal to zero. So if we're looking for just s of x, the denominator x cannot equal zero. Again, just looking at the first function. The second function, do we have any restrictions? Well, t of x is linear, meaning that the degree of x is 1. Linear doesn't have restriction. Or does not have any restrictions. Therefore, the domain is all real numbers, right? It's everything can work for the second function. Now, the third function, the domain of r of x, if we look at it carefully, r of x is a quadratic function. Excuse me. We have over here that r of x is quadratic. And quadratic functions, the domain is also all real numbers. So in reality, the only restriction that we have is s. But we're doing a few things with these functions where we have 8, 9, and 10. So we have a few things that we're going to do. We're going to subtract r and t. So we have r minus t of x is equal to r of x minus t of x. And then we're going to look at the domain of each of them. Well, R does not have a restriction. R is quadratic. It's all real numbers. The domain of R of x and T of x do not have restriction. So the subtraction between the two values, so we have R of x. So R of x is, if we rewrite it, we have x squared plus 3. That's going to be subtracted by x plus 4. Then we clean it up, we're going to get x squared. So here we're going to distribute that negative. So we have x squared plus 3 minus x minus 4. If we rewrite that, that's an x squared. And then we have minus x, and then we have a minus 1. Well, we have a quadratic. That means that the domain of that quadratic will also give us all real numbers. So we evaluate it, and we also write the domain of the function. And then likewise, we have a similar example. So then we have what happens if we have r of x over t of x. So r of x over t of x. Now r in this case is x squared plus 3 over x plus 4. Now, if we're looking for the domain, this becomes now a rational function. And we have to find, okay, well, what's the denominator? You're not allowed to be 0 on the denominator. So this becomes an equation. Where, at what value does that denominator gives us 0? So that's x plus 4, set it equal to 0. That gives us x equal negative 4. So at x equal negative 4, that will make my denominator 0. So that means that my domain is every value, negative infinity to negative 4 union from negative 4 to infinity. And that's because we had to find, okay, what denominator, what value will make my denominator 0? That value is negative 4. That means that when you're looking for the domain, it can be any value except where it makes that denominator 0. And this is my solution in interval notation. And then last but not least, we have number 10. That means that we're going to multiply s of t times, s of x. So we have s of x times t of x. And then, well, remember that s of x was 2 over x, right? That's over here. And then we're going to multiply that by t of x, which is x plus 4. So if we multiply it out, we get 2x over x plus 8 over x. If we simplify that, that's 2, just a 2, plus 8 over x. And then what is allowed or what's not allowed in my denominator, x cannot equal 0. So then we have to make sure that we state that. The fact that x cannot equal 0. So then the domain is all real numbers except 0. And that would be the solution for number 10. So hopefully, as we're progressing, we understand we had to look at each individual function first, identify its own domain, and then kind of build up from there. Now let's talk about evaluating a difference quotient and what does that mean. So we've seen so far what is the slope of a line, rise over run. Well, what happens when we have a curve, let's say this function y equal f of x, and we want to find the domain, we want to find the slope of that line. Well, it's not going to be necessarily rise over run, but it's actually going to be some values evaluated at some particular location. So here we have a distance between x and x plus h, where we have the first point evaluated at x, the other point as it moves along this h units, it becomes f of x plus h. So it's a new value. So this expression of f of x plus h minus f of x all over h is called a difference quotient. And by definition, that gives you the value of a secant line. So let's say that we're asked to find just f of x plus h. So f of x plus h and f of x is given. Well, if we're looking for f of x plus h, we're substituting first. Everywhere we see an x, we're going to put x plus h. So it's going to be 5 times x plus h minus 2. And then we're going to go ahead and distribute. And this will give me my f of x plus h. Now we're going to have to use this definition to use that secant line or that difference quotient. So I have to say, okay, well, I need f of x plus h minus f of x all over h. Okay, so let's rewrite it. I already know what f of x plus h is. That's 5x plus 5h minus 2 minus the quantity f of x. So the quantity of f of x is 5x minus 2 all over h. We're going to have to distribute this negative, and we're going to get 5x plus 5h minus 2 minus 5x plus 2 in the numerator all over h. Okay, now we have to clean up. I have a 5x and a minus 5x that will cancel. I have a minus 2 and a plus 2 that will also cancel. I'm going to be left with 5h over h. That simplifies to just 5. So my solution would be 5. Now I'm going to do that same thing, but now with a harder equation. So again, I'll start slow by identifying, well, what's 5 f of x plus h? Again, wherever I see an x, I'm going to be placing x plus h. So looking over here, I have x plus h quantity squared minus 3 times x plus h plus 8. I'm going to have to do a binomial here, multiply. Well, what's x plus h times x plus h minus 3x minus 3h plus 8, right? So right now, I actually distributed this minus 3 here. And then I have to clean up x squared plus 2xh plus h squared. How did I get that? Multiply x times x, x squared. I have hx and hx, that's 2xh's, and then h and h, that's h squared, minus 3x minus 3h plus 8. So all of this is f of x plus h. So I'm going to use that to substitute that for my difference quotient. So I'm going to have x squared plus 2xh plus h squared minus 3x minus 3h plus 8. All this minus f of x, which was x squared minus 3x plus 8 all over h. I'm going to have to distribute this negative and clean up my values. So I'll have x squared plus 2xh plus h squared minus 3x minus 3h plus 8 minus x squared plus 3x minus 8 all over h. And then remember, this negative distributed everything in there. Then I started to notice I have a positive x squared and a negative x squared. I have a minus 3x and a positive 3x. I have a plus 8 and a minus 8. So what I have remaining, I have 2xh plus h squared minus 3h all over h. I can factor, they all have an h in common that I can pull out. And I'm going to do that. So I'm going to factor out. So factor out that h in the front. So I have h to be 2x plus h remaining minus 3 all over the h that was on the denominator. That will cancel, and I'm only left with 2x plus h minus 3. And that will be my solution for that particular difference quotient. Okay. And that's for a quadratic. So it's definitely much more work, but definitely doable. So hopefully you are tracking the notes and you're following along the distributions of those negatives, because that can also happen. Alrighty, let's talk about compositions of functions. So the way that composition works is you are substituting a function within a function, which we already kind of did that when we did f of x plus h's on that previous example. So we want to know what's the composition. So if the order matters, so if it looks like this, you have f composing g. If it looks like this, and if you have g of f of x, then you have g of f of x. So it's definitely order matters. So the first part is f of g of x. So you have f of g of x. That means you're substituting the function g into f. So this is f of 5x plus 4. So everywhere you see an x in f, you now put 5x plus 4. So you'll have 5x plus 4 quantity squared minus 3 times 5x plus 4 plus 1. That's not solving anything. That's just substituting. Of course, I'm going to have to multiply this out. So I have 5x plus 4 times 5x plus 4 minus, I'm going to go ahead and distribute this minus 3. So it's minus 15x minus 12 plus 1. And then I have to do my cleanup over here. So 5x times 5x, that's 25x squared. I have a plus 20x plus another 20x plus 16 minus 15x minus 12 plus 1. Now I have to do bookkeeping. So I have a quadratic term here. I have 40x and then a minus 15. That gives me a positive 25. So I'm going to rewrite it over here. So 25x squared plus 25x, right? Because this is 40 minus 15, that's 25. And then I have a 16 minus 12, that's a 4 plus 1, that's a plus 5. And there is my solution after doing some cleanup. Now, the other way around, now what if it's if it's g of f of x? Now you're substituting x squared minus 3x plus 1 into the function g. So it should look like 5 times the quadratic x squared minus 3x plus 1 plus 4 because you're substituting into this x. And then you're going to do some cleanup. 5x squared minus 15x plus 5 plus 4. Now this gives you 5x squared minus 15x plus 9. See how the answers are different? And they should because it's not commutative. So f of g, it's not the same as g of f. So this is called compositions of functions. Alrighty, let's look at number 14. Number 14, you're composing f of g of x. And if we look at this carefully, we have f of the square root of 5x plus 5. Now, the inside of a square root is always positive, so we have to just take that into consideration. So we have 5 times the square root of 5x plus 5 quantity squared minus 1. What do we know about square roots and quadratic values? They cancel each other out. So I have 5 times 5x plus 5 minus 1. So if I do some cleanup, I get 25x plus 25 minus 1. That gives me 25x plus 24 to be my final answer. Now, on the other hand, I have g of f of x in here. So it's g of 5x squared minus 1. So now I have everything under a root. I have 5 times 5x squared minus 1 plus 5. I'm going to work inside a root. I'm going to distribute this 5 that I have. Hopefully that's visible. That's 5. It's going to distribute to be 25x squared minus 5 plus 5. This gives me the square root of 25x squared. You're going to say, okay, well, we can split that as 25 and the square root of x squared. This is 5, and then be careful here because x can be positive or negative, but because we are inside a root, this will be the absolute value of x. So by definition, whenever we have the square root of an x squared term, we have to make sure that we identify that we're only looking at the positive side. X is strictly greater than 0 because it's inside a root. So we have to have the solution of that absolute value. Moving on to question 15. So hopefully you guys are tracking all of the notes and the solutions. Now let's evaluate. Now this one's a little bit different because it's asking you to evaluate it at a particular value. So this means f of g of 9. So you first have to find g of 9, which is going to be 2 times 9 minus 8, which is 18 minus 8, which is 10. That means you're going to have to use this number and now plug it into f of 10. So you're going to have to do double work. So f of 10 is 3 over 10 minus 4, which is 3 over 6, or 1/2. And that's my final answer. 1/2 is the solution. But you needed to find g of 9 first to get to a half. So this means g of f of 6. So you first find f of 6 into the equation. So that's 3 over 6 minus 4. This gives you 3 over 2. So you're substituting 3/2 into g. So g of 3/2. That's what you are actually evaluating. So then that gives us 2 times 3/2 minus 8. Well, this gives you 6 over 2, or just 3 minus 8. And that's 3 minus 8 gives you -5. And then let's see here. And that's my solution, -5 for this particular answer. So let's look at number 16. So by now, hopefully you guys feel comfortable doing compositions of functions. And we do have a few more before we finish this second part of lecture. So given f and g, find f of g and the domain of f and g. So first we are asked to find f of g and then looking at the domain. So first of all, again, I like to look at them separately, individually first. So I like to look at the domain of them separately. So let me go back and then, so the domain of f individually, so the domain of f of x separately, and then my pencil doesn't want to help me today. The domain of f of x is that x cannot equal -2. It can be everything except -2, right? We talked about the denominator cannot be 0. But now g of x is linear, so you don't have any restrictions. The domain of g is all real numbers. So if we do, okay, f composed with g of x, well, g doesn't have any restrictions, so f of 3x minus 2, if we substitute it, that gives us 3 over 3x minus 2 plus 2. So this is 3 over 3x or 1 over x, where x cannot equal 0. So the restrictions are two restrictions. X cannot equal 0 and x cannot equal -2. And that's from the initial f because it was rational. So the domain is everything except 0 and -2. So from negative infinity to -2, union from -2 to 0, union from 0 to infinity. So we have to take into consideration both restrictions, the original restriction of f and the composition. Now, when we have number 17, well, h itself has a restriction. Remember, the inside of a root 3x minus 7, go back here, 3x minus 7 has to be strictly greater than or equal to 0. So if we evaluate it, 3x is greater than or equal to 7. X should be strictly greater than, 7 over 3. So then the domain of at least h is that the value of x should be strictly greater than or equal to 7/3. Now, if we want to have the composition, oh, they're saying that h of x is the composition between two functions. Okay, so who's your inside and who's your outside? So you actually, this is called decomposing. You want to decompose. So this is the composition between two functions, f and g. So the inside function, it looks like it's going to be 3x minus 7. So this one, they didn't ask to find the domain. It just said to decompose. So the inside function, is going to be, one second here. So the inside function is the 3x minus 7, where the outside function is the square root function. So then if we have f of g of x, who's the inside? G of x is the inside, which is 3x minus 7, and f of x is the outside, which is the square root of x. So what you're doing is, you know what the solution is, now you want to split it apart. Who's the inside and who's the outside? Same thing here. You want to find the two functions you want to decompose. So here you have an outside And then inside, it looks like you have the inside to be x plus 1. And then we have an outside. So it's usually the inside, it's usually what's in the parentheses and a square root and an absolute value. That's usually your guidance. So your outside, it looks like an equal cubic plus the 8. The 8 is just floating around. So then again, if I have f of g of x, the inside function g of x is going to be x plus 1, since that's what's in the parentheses. And then f of x would be my cubic function with the 8 that's floating around. That 8 value that's floating around. Now, when we're looking at question number 19, we have to look at a particular graph. So this means we want to find f of 3 minus g of 3. So f of 3, we have f evaluated at 3. So 1, 2, 3. If we look at that value corresponds to 1, 2, 3. So f of 3 is 3 minus g of 3. So now we're going to go to g, which is so let me go back. F is the blue. So when f is 3, 1, 2, 3, yes. So f of 3 is 3. And then g of 3, the red one, is 1, 1, 2, 3, which is also 3. So the first one, f of 3 for one of the values. Oh, I'm not seeing properly. F of 3, 1, 2, 3. Sorry about that. So f of 3 is actually 4. It's up right here. F of 3 gives you 4 as my y value, and g of 3 is actually 3. So then we subtract 4 minus 3, and that's going to give us 1. Just looking at the graph. Now the next one is g of negative 2 divided by f of negative 2. So g of negative 2, there's my g. 1, 2, bring it all the way down. That looks like negative 4. All over f of negative 1. Oh, sorry, f of negative 2. So negative 2, it's up here at 1, 2. So then you divide negative 4 by 2. That's negative 2. And then you have g of 1. Oh, sorry, this is a composition now. So this is not multiplication. This is a composition. So this is g of f of 1. So first you have to compose or find f of 1. F of 1, it's the blue f. F of 1 is 2. So then this is actually g of 2. So g, the blue, at 2. 1, 2, 3, 4. So you look at the graph. So technically, my solution is 4. So you have to first do f of 1, that gives you 2, and then g of 2, which is 4. And then D and E are very similar. You have to do composition of f composed with g at negative 3. So we have f of g of negative 3. So first we need to find, okay, what's g at negative 3? So let's go into their graph. G, 1, 2, 3, it's down here. It's going to be negative 4. And then you need to find f of negative 4. So that's my f at negative 1, 2, 3, and 4. And what does that give me? Negative 2. You're going to say, oh, I see an arrow. Yeah, but it's going to cross that negative 2 value. And last but not least, on E, we have f of negative 3. F of negative 3. F is the blue. I have 1, 2, 3. That's 0. So f of negative 3 is going to give me 0. So what's f of 0? F of 0 is actually positive 2. So 0 go up, it hits at 2. So you're going back and forth between the function and the graph and the function. And that gives me the solution for question 19. And we have one more, which is question 20. So let's go ahead by reading the question first. A party balloon is being filled with helium. As the balloon is filling, the radius of the balloon is changing at a rate of 3 inches per second. So we have a radius that's given, a radius. They're giving us a rate, an increasing rate that's increasing at a particular rate. And as it being filling, when you're inflating a balloon, that means a volume. So we're going to have to deal with all these things together. We're going to look at the volume, a particular radius, and a particular rate. So the first question is saying we want to write a function that represents radius of the balloon r of t after t seconds. So r of t is the rate that's increasing, and it's increasing at a rate of 3 inches per second. So it's going to be 3t. It's a function of time. So that's why it's saying after t seconds. Now, part B, it says write a function expressing the volume in terms of r, v of r. So remember, well, we have to know, well, what's the volume of a sphere or a balloon? V is equal to 4 over 3 pi r cubed. You don't have to memorize it by heart, but this is a formula that you should already know. A volume of a sphere, a volume of a cylinder. In case that it doesn't happen, let's say that you're on a test, that's probably going to be given to you. But I would just to memorize it just to be safe. Now, if they're saying evaluate V of R of T, that means you have V of R of T, you have a composition. So then you're going to evaluate R of T in for R in terms of a function of T. So you have V of 3T. So everywhere we see an R, we're going to put 3T. So that's going to be 4 over 3 pi times 3T cubed. So when we evaluate, I get 4/3 times 27T cubed pi. So then if we clean it up, I have a 27 over 3, that's 9. So 4 times 9 pi t to the cubed, which is 36 pi t cubed. And then remember, this is a volume in terms of time. That's why we have a t. So now what happens if we evaluate it? What v of r of 2? So first we do r of 2, which is, sorry, we use r of t to be 3t. So r of 2 would be 6. So then you would have to, let me change this. Well, we already know what v of r is in terms of the value. So let me change it. So we're going to use that previous information of my 36 pi t cubed because the t is already given. So t is the seconds. So then we have 36 pi times 2 to the third. So that's going to be 36 times 8 pi. And that gives us 288 pi or 904.32 centimeters cubed. Or sorry, centimeters. Let's see. This is inches cubed. Sorry. So the units are inches. So what is that inches cubed, which is our units, or cubic inches? So this means that after 2 seconds, the balloon or the volume of the balloon is now 904.32 inches in terms of the volume. cubic unit, cubic inches or inches cubed. And that's what represents this question. And with that, we terminate section 1.8. So what we finalized is we talked about the domain, we talked about composite functions, difference quotients, and applying and doing an application of a composition of functions, identifying how to compose and decompose and evaluate. Alrighty, so hopefully we're good to go on section 1.8. Thank you, and that terminates chapter 1. Thank you. Bye-bye.